What if a few LEDs and a buzzer could act like a real traffic safety system? In this project, you'll wire an ESP32, control red, yellow, and green signals, and add sound alerts through code. We've already built the big picture. Robots take in information, process it, and then act. The ESP32 is the controller that handles that thinking and sends signals to real components. Now we shift from understanding to building. You'll make outputs respond with LEDs and a buzzer before we add sensors in the next projects. Your mission is to build a mini traffic signal system, similar to the ones people use every day. 3 LEDs will send visual messages. Red means stop, yellow means caution, and green means go. A buzzer adds sound, like a warning or crossing signal. Together, these outputs show a key idea in embedded systems: communicating clearly with people. Before wiring, let's review each part's job. The ESP32 is the controller, or brain. It runs the program and decides which output turns on. The LEDs become the traffic lights, showing red, yellow, and green states. Each LED needs a resistor to limit current and protect the circuit. The buzzer adds sound for alerts or feedback. The breadboard, jumper wires, and USB cable help connect and power everything. An LED is directional, so wiring it backward is a common beginner mistake. The positive side is the anode, usually the longer leg. The negative side is the cathode, usually the shorter leg, and often marked by a flat edge on the plastic body. For the LED to light, current must leave the ESP32 output pin, pass through a resistor, enter the anode, exit the cathode, and return to ground. The resistor is not optional. It protects both the LED and the ESP32 pin by limiting current. Think of a resistor as a speed limit for electricity. An LED needs current, but too much can overheat it, burn it out, or stress the ESP32 pin. In beginner LED circuits, a 220 ohm or 330 ohm resistor is commonly used to keep current at a safe level. When you connect multiple LEDs, give each one its own resistor, so every light is protected. A breadboard is a reusable wiring shortcut. You plug parts into holes, and hidden metal clips underneath connect certain holes together. In the main area, holes in the same numbered row are connected in small groups, so component leads in that group share the same electrical point. The long rails are usually used for power, one for voltage, one for ground. Always check which holes are connected before inserting wires. If voltage and ground are accidentally linked, you create a short circuit, which can heat or damage parts. When code controls an output, it changes the voltage on a GPIO pin. GPIO stands for General Purpose Input-Output, and pins like 16, 17, 18, or 19 can be assigned to drive devices. Setting a pin high sends a voltage signal, so an LED can light or a buzzer can sound. Setting it low removes that signal and turns the device off. The key wiring rule is shared ground. The ESP32 and every output component must connect to the same GND, or the signal has no reliable reference. For each traffic light LED, the ESP32 output drives the anode through a current-limiting resistor. Start with the red LED, then repeat the same pattern for yellow and green, using a separate GPIO pin for each one. The cathode side of every LED goes back to ground, creating a common return path. Match wire colors to the LED colors, and use black for ground. Before powering up, check resistor placement and LED polarity. A reversed LED simply will not light. So far, output may have felt like simply turning an LED on. A buzzer expands that idea. The ESP32 sends an electrical signal, and the component converts it into sound. With an active buzzer, the wiring is straightforward. Connect the positive pin to a GPIO, such as GPIO 19, and the negative pin to GND. Then your code can switch that pin on to make a beep. Always check polarity and current rating. If the buzzer needs more current than the ESP32 pin can safely supply, use a transistor driver. Timing logic turns separate LEDs into a believable traffic signal. Instead of turning everything on at once, the program holds one state for a set time: green for 10 seconds, yellow for 3, then red for 7. During red, the buzzer can beep as a warning. In code, each state is usually followed by a delay or timing block. Change the delay values, and you change the behavior of the whole system without rewiring the circuit. Next, connect the program to the hardware. Give each output a clear variable name, like red LED or buzzer, and assign it to the ESP32 pin it is wired to. In setup, pin mode tells the board those pins will send voltage out, not read input. After that, digital write controls the behavior. High turns an LED or buzzer on, and low turns it off. When testing, start with one output at a time. That makes wiring mistakes and wrong pin numbers much easier to find. Now the pieces become one repeating behavior. Each traffic state turns on one LED, waits, then turns it off before the next state begins. Green stays on the longest because cars are allowed to go. Yellow uses a shorter delay to warn that the state is changing. Red turns on for stop, and the buzzer briefly turns on with it to create an alert. Because this code runs inside loop, the Arduino automatically starts over after red turns off, producing a continuous traffic light cycle. When something fails, debug calmly and change only one thing at a time. If an LED stays off, check its polarity, confirm the resistor is in series, and make sure your code uses the correct GPIO pin. If the whole circuit is dead, check USB power and verify that every component shares a common ground. For a silent buzzer, check polarity, then confirm whether it is active or passive. Once it works, you can improve the project by adjusting timing, adding a pedestrian mode, or creating warning blink patterns. You've built your first ESP32 output system, safe LED circuits, timed traffic light logic, and buzzer feedback. You also practiced the core pattern of physical computing. Wire the hardware, write the code, and test the behavior. Next, we'll move from outputs to inputs, using sensors, so projects can respond to light, temperature, humidity, and the world around them.